The shortest distance in this story is the one that causes the most confusion. Amazon's data center campus sits beside the Susquehanna nuclear plant in northeastern Pennsylvania. Two cooling towers dominate the site. Transmission lines leave the switchyard. The server campus is close enough to make a simple promise sound obvious. Put the computers next to the reactors and send nuclear power directly across the fence. That was the original idea. Part of the campus load sat behind the plant's generation meter, but in April 2026, the arrangement changed. Susquehanna now supplies electricity to the PJM grid. Talen acts as Amazon's retail generation supplier. PPL handles transmission and delivery to the campus. The buildings did not move. The reactors did not move. The contract still ties Amazon to as much as 1,920 megawatts of Susquehanna's output over time. What moved was the electrical and commercial boundary. If the data center is beside the plant and has a contract for its power, why put the grid between them? The answer is not that regulators oppose nuclear power or data center co-location. It is that a generator and a giant load can use the regional system even when very little energy appears to cross the property line. The grid balances the plant, supports the load, carries power when one side changes, and provides a market for output the campus does not take. That service has a cost. The fight was over how to measure it, who should pay it, and whether a private wire could make a public obligation disappear. Susquehanna is a 2-unit boiling water nuclear station in Salem Township, Pennsylvania. Its nameplate capacity is roughly 2.5 gigawatts. The plant entered service in the 1980s and now supplies a large block of steady generation into PJM, the regional system covering all or parts of 13 states and the District of Columbia. Beside it is a campus built for a very different kind of machine. A nuclear unit produces power through steam, a turbine, and a large rotating generator. A data center consumes power through thousands of rectifiers, power supplies, processors, cooling systems, and backup devices. Both can operate continuously, but they do not behave the same way. A reactor changes output under strict operating limits. A data center can add halls and phases, transfer load between facilities, or change its demand much faster. If a server hall trips, the generator does not instantly reduce nuclear heat by the same amount. If a nuclear unit trips, the campus still expects uninterrupted electric service. Inside the plant, nuclear heat boils water into steam. Steam turns the turbine turns the generator, and the generator produces alternating current synchronized with the regional system. Plant transformers raise the voltage for transmission. Breakers in the switchyard can isolate a fault without taking every connected line out of service. Inside the campus, the sequence runs the other way. High voltage power is stepped down, switched through redundant paths, and converted for computing equipment. Uninterruptible power systems keep the electronics stable through short disturbances. Engine generators can carry critical load during a longer loss of utility supply, but they are not a permanent substitute for a 1,920 megawatt power contract. The plant therefore produces one large synchronized waveform while the campus divides power into thousands of controlled electronic loads. Between them, meters record energy, protection systems watch current and voltage, and operators need to know which equipment will respond first when something changes. The grid sits between those time scales. Start at the plant generator. Electricity leaves at generator voltage, passes through a step-up transformer, and enters the high-voltage switchyard. From there, breakers and transmission lines connect Susquehanna to PJM. System operators constantly balance all generation and demand across the region. Now add the campus. In a traditional front-of-the-meter arrangement, the plant injects power into the network. The utility measures the data center as a retail load on the other side of the delivery system. A commercial contract can match the plant's output to the buyer's consumption, but the physical grid still carries and balances both. Behind the meter, part of the load is placed on the generator side of the ordinary retail measurement boundary. The plant's metered injection into PJM is reduced by the power consumed locally. If the generator produces 1,000 megawatts and the co-located load takes 300, the meter may show 700 megawatts entering the regional system. That can be efficient. The local load may avoid some transmission withdrawals. The system may need fewer upgrades than if the same 300 megawatts appeared as ordinary network demand somewhere else. But the plant and campus are not an isolated island. They remain synchronized to PJM. The frequency reference, contingency support, market dispatch, and emergency paths still come from the larger system. That is the central tension. A meter can show little grid withdrawal while the physical arrangement still relies on the grid being there. Amazon bought the adjacent campus assets from Talen in March 2024 for a gross price of $650 million. The sale came with a power purchase agreement tied to Susquehanna. The original interconnection arrangement allowed up to 300 megawatts of campus load behind the plant meter. Talen, Amazon, and PPL later sought an amendment that would have raised that amount to 480 megawatts. FERC rejected the amendment in 2024. The rejection did not say a data center could never sit beside a generator. It turned on the specific agreement and the rules then on file. PJM's tariff did not clearly describe all the rates, terms, and conditions for a generator serving a large co-located load while remaining connected to the regional system. That gap matters because an interconnection agreement was originally written to connect a generator. Expanding it to govern a huge new customer can change more than a wire. It can affect how much generation PJM counts, how much load appears in the forecast, what transmission service is reserved, and which customers pay for shared system functions. The parties argued over jurisdiction too. States regulate retail delivery. FERC regulates interstate transmission and wholesale power. PJM administers a regional tariff. A private power contract can cross all three without fitting neatly inside any one document. The legal dispute continued, but the commercial arrangement changed. In June 2025, Talen and Amazon announced a revised power purchase agreement for up to 1,920 megawatts through 2042. The quantity ramps over time and is expected to reach the full level no later than 2032, with the possibility of accelerating. It is a ceiling and schedule, not a claim that the campus draws 1,920 megawatts continuously today. The revised structure replaces the disputed behind-the-meter path with front-of-the-meter service. Talen's May 2026 filing says the transition occurred in April. The switch also gives the contract more than one possible delivery point. Talen's filings say the power can serve the adjacent campus and other Amazon locations in Pennsylvania. That matters because the commercial agreement is no longer confined to a private-looking path between two neighboring properties. It can match Susquehanna generation with Amazon load elsewhere on the same utility and regional system. The schedule remains gradual. Full quantity is expected no later than 2032, so planners do not model the entire 1,920 megawatts as if it appeared in one night. They use a ramp, just as the plant owner uses the ramp to forecast contracted sales. If Amazon accelerates, the delivery system and market obligations have to keep pace. The timing overlapped with a planned refueling outage on Susquehanna Unit 1. The unit shut down on March 23rd, and Talen expected the work to finish in the first half of May. The public filing does not provide a cable-by-cable construction diary, so the film should not invent one. It does confirm the result. The commercial and metering arrangement had changed. Susquehanna now puts its power into PJM. Talen supplies Amazon as a retail generator. PPL transmits and delivers the electricity. The campus is still beside the plant. The grid is now explicit in the transaction. Moving the meter boundary changes what the regional system can see. Under the earlier setup, the local campus reduced the amount of Susquehanna generation recorded as entering PJM. Some of the load did not appear in the ordinary regional load forecast in the same way as front-of-the-meter demand. When the arrangement changed, that load moved into PJM's forecast. The plant's output and the campus demand became separate measured quantities. Operators could plan around the full load and the full generator instead of treating part of one as a subtraction from the other. The change also affected capacity. Energy is the electricity produced over time. Capacity is a commitment that a resource can be available during a future delivery period. PJM runs auctions to secure enough capacity for peak demand and contingencies. Transmission service is a third quantity. It describes the right and obligation to move power through the network under stated conditions. A customer can buy energy from one plant, contribute to capacity needs through the regional market, and reserve transmission delivery from a utility. Those payments can appear together on the same project while measuring different services. When part of Susquehanna's output was committed behind the meter, PJM did not count all of that generation as available to the capacity market. After the load entered the forecast, PJM asked FERC to restore 148 megawatts of Susquehanna capacity interconnection rights. FERC approved the request, making that amount available for the 2027-2028 capacity auction and later auctions. Nothing physical was created by changing the accounting. The 148 megawatts did not appear from a new turbine. The regional market could count it differently because the campus and plant were now represented as separate load and generation. The same separation clarifies 3 operating days. On an ordinary day, both units may run while the campus follows its ramp. Susquehanna offers power into PJM. Amazon buys under its contract. PPL meters and delivers the campus load. The commercial agreement can match the quantities even though the physical network mixes this generation with every other injection and withdrawal. During a planned refueling outage, one reactor is unavailable for weeks. Talen still has a supply obligation under the terms of its agreement, while PJM dispatches the rest of the region and PPL continues delivering to the campus. The exact commercial settlement depends on the contract, but the physical point is plain. Adjacency cannot make a reactor produce while it is shut down. During an unplanned trip, the change happens in seconds. Susquehanna's measured injection falls. The campus remains visible as demand. PJM's frequency response and reserves begin correcting the imbalance before any human can renegotiate a schedule. If the campus has agreed to curtail, its load reduction can become part of that response. If it has firm service, the network must keep supplying it within the service terms. The front-of-the-meter model does not guarantee that every contingency is easy. It gives operators the two values they need to study it: the generator that can disappear and the load that may remain. Those values need real telemetry, not an annual estimate. Operators need the campus demand, the plant output, breaker status, and the amount of load available to curtail. Protection settings have to distinguish a short voltage disturbance from a true loss of supply. Reconnection must be controlled so thousands of servers do not return as one sudden block after the system has already balanced around their absence. A service can be flexible only when the flexibility is measured and tested. That is one reason meter location matters. It changes the model used to answer two different questions. How much power is the plant offering to the regional system? How much demand must the system be ready to serve? With both quantities visible, PJM can study the loss of either side. If the data center suddenly reduces consumption, the grid absorbs the generation surplus. If a nuclear unit trips, the grid must replace the missing supply, or the campus must curtail under its service agreement. If the campus ramps faster than planned, PPL and PJM see the demand against the network. The contract still matters. Amazon can buy carbon-free power from Talen over a long term. That revenue can support continued operation of the nuclear plant. But a power purchase agreement is not a private extension cord. It assigns financial rights and obligations. It does not label each electron with a destination. There is also a practical difference between a power contract and retail delivery. The PPA says who supplies the energy and how the buyer and seller settle it. The delivery tariff says how the customer connects, what demand the system prepares for, what service can be interrupted, and which charges apply. A strong energy contract cannot replace a missing transmission service definition. At every instant, the grid follows physics. Power takes the available paths through the network. Meters and contracts reconcile who produced, consumed, and paid for it. Co-location has a legitimate engineering advantage. A controllable data center beside a generator can limit how much it withdraws from the regional grid. If the arrangement can reduce demand during stress, PJM may avoid some network upgrades or new capacity. FERC recognized that advantage in its December 2025 co-location order. It directed PJM to create clearer transmission options for customers that can control their withdrawals. One option can be firm. Another can be non-firm, meaning the customer accepts limits when the system cannot support the requested withdrawal. This is more precise than pretending every co-located load is either fully private or an ordinary network customer. A campus that guarantees it will never draw more than 50 megawatts from PJM does not need the same service as one that expects all 500 megawatts to remain available through the grid after the plant trips. The first can accept curtailment. The second asks the network to act as a full backup power source. Picture the second case during a reactor trip. Before the event, the adjacent generator and campus may look almost balanced. The plant trips in a fraction of a second, the data center load remains. If the campus has firm network service for its full demand, power must immediately arrive through other transmission paths while regional reserves replace the lost generation. Lines and transformers have to be sized for that transfer even if it happens rarely. Now picture a non-firm campus. Its controls reduce computing demand as soon as the generator is lost. Batteries can bridge the command, workloads can move, and backup engines can start. The grid may supply only a limited contract amount. That promise can avoid a full-strength backup path, but only if the reduction is fast, measurable, and enforceable. The difference is not the campus address. It is the behavior written into the service. One arrangement asks PJM to replace the plant. The other asks PJM to manage a controlled reduction. The problem is the middle case. Suppose a data center normally takes nearly all of its power from the adjacent generator. Its metered network withdrawal is tiny, yet the generator and load remain synchronized through PJM. The plant relies on the grid for stable operation and a market for excess output. The campus benefits from a system that can carry power during maintenance, faults, and imbalances. Both benefit from regional operators, protection coordination, and restoration plans. How much should that invisible support cost? Commissioner Chang argued that a co-located load could pay very little if its charge were based only on measured withdrawals, even though the arrangement could not operate as intended without the transmission system. She asked whether PJM needed a minimum charge for that reliance. The question is difficult because the grid is not one service. Transmission lines move bulk power. Frequency regulation corrects short imbalances. Reserves stand ready for sudden losses. Black start resources help restore the system after a collapse. Planning and control centers keep the network inside limits. A customer may use little energy from the grid while still benefiting from several of those capabilities. At the same time, charging the co-located load as though it always withdrew its full demand can erase the efficiency that made co-location attractive. If the campus can curtail during a plant outage, the system may not need to build a full backup path. A rate that assumes full firm service would make it pay for capacity it agreed not to use. FERC's task is to price the actual promise. How much can the campus withdraw? How fast must it curtail? What happens when the generator trips? Which network upgrades are avoided? Which system services remain necessary even at zero withdrawal? Those are engineering questions before they become billing questions. Talen's case is straightforward. A long contract gives Susquehanna a stable customer for carbon-free electricity through 2042. The plant keeps selling into PJM, so its output remains visible to the regional market. The agreement can support continued operation and possible investment in more generation. Amazon's case is also clear. The company gains a large, long-term power supply for AI and cloud facilities. The campus remains beside an existing nuclear station, instead of depending entirely on new fossil generation built for one customer. PPL argues that front-of-the-meter service helps the wider network. Large customers pay significant transmission charges. The utility says those contributions can lower the transmission component of other customers' bills while supporting grid investment. That is a company claim, not a guaranteed household saving. Whether bills fall depends on the new revenue, the upgrades required to serve the load, and the other costs entering rates. The carbon claim needs the same discipline. Susquehanna is a nuclear generator with no combustion emissions during operation, and Amazon can contract for its output. That does not mean the campus is physically isolated from every other generator in PJM at every second. During outages and market imbalances, power can arrive through the regional system. Contract accounting and annual energy matching answer a different question from instantaneous electric flow. The agreement can still have a real effect. A long-term buyer can reduce the plant owner's exposure to volatile wholesale prices and support investment in the existing units. The accurate statement is that Amazon buys contracted carbon-free nuclear supply from Talen while remaining connected to the regional grid. The counter-argument is not that Amazon should be denied power because it is large. It is that a 920 megawatt contract can reshape a regional market even when delivery ramps gradually. If Susquehanna sells more output under a long-term private agreement, less of its energy may be exposed to short-term market prices. If the campus adds load, PJM must plan enough generation and transmission for that demand. If the contract supports the plant's continued operation, the region retains a large nuclear resource that might otherwise face more market risk. Each effect can be true at the same time. The public interest test is therefore concrete. Does the campus pay for the transmission service it actually requires? Does its flexibility genuinely avoid equipment and capacity, or does the grid still prepare to serve the full load? Are plant output and campus demand visible in regional forecasts? Who carries the cost if the ramp changes? The April transition improves the visibility part. It does not settle every future rate. The meter in this story is more than a box that records kilowatt hours. On one side, a co-located load can appear as a reduction in plant output. On the other, the same campus appears as a customer the regional grid must plan to serve. Moving that boundary changes capacity accounting, forecast treatment, and the transmission service attached to the load. It also makes the physical contingency easier to explain. Begin with both nuclear units running and the campus taking power. If campus demand falls, more Susquehanna output flows into PJM. If one reactor trips, less power enters the grid while the campus remains a measured load. The regional system sees both movements and balances them. In a behind-the-meter diagram, the same events can be compressed into one net number at the interconnection. That is not wrong. Net metering is useful, but the net value can hide the size and behavior of the two machines behind it. For ordinary rooftop solar, that hidden detail is small. For a nuclear plant beside a campus that may eventually contract for 1,920 megawatts, it is a grid-scale distinction. This is why the national co-location debate expanded beyond Susquehanna. Data centers are looking for faster power. Existing generators are looking for long-term customers. Utilities are trying to build enough delivery infrastructure without assigning private risk to everyone else. Co-location can solve part of the timing problem. A generator already exists. The site already has transmission. A flexible campus may accept interruption instead of waiting years for full network service. But adjacency does not repeal system physics. The plant still needs somewhere to send power when the campus takes less. The campus needs a plan when the plant produces less. The switchyard must survive faults. Operators need telemetry. The regional market needs to know which megawatts are generation, which are load, and which can vanish under a contingency. Front-of-the-meter service makes those obligations explicit. Better co-location rules may later allow some of them to be priced more narrowly. So why did Amazon's nuclear data center move on to the grid? Because the grid was already part of the machine. Susquehanna and the campus were physically close, but they were not self-sufficient. The plant relied on PJM for synchronization, balancing, and a destination for unused output. The campus relied on a system that could deliver power and manage the loss of either side. The earlier agreement did not clearly assign every service and cost under PJM's tariff. The April 2026 transition separated the two quantities. Susquehanna supplies PJM. Amazon appears as a load in the forecast. Talen remains the contracted supplier. PPL handles transmission and delivery. That does not make the nuclear contract meaningless. It makes the contract more honest about the network around it. The minimum safeguard for the next co-located data center should follow the same physical logic. Show the whole plant and campus, measure generation and load separately, define the maximum grid withdrawal, state the curtailment promise, price the system services that remain, and publish who pays for each upgrade. A data center can sit behind a meter. Its consequences cannot.